Hi everyone, welcome. The purpose of this video is to go through a couple problems in the mixed conversion factor practice. So let's jump right in. Question 6, how many atoms of nitrogen are present in 5.0 grams of atmospheric nitrogen? All right, let's take a look at this. So we're going to start with starting unit, final unit, and then figure out the conversion factors that we need. So my starting unit is grams of atmospheric nitrogen. So grams of nitrogen, and nitrogen in the atmosphere, nitrogen is diatomic, exists as N2. Final unit. My final unit is individual nitrogen atoms. So just atoms of N. So conversion factors. Well, I'm going to need to get from grams into moles because moles are the unit that I use to compare different things. And I see I have two different things here, a molecule of nitrogen and nitrogen atoms. So grams of N2 into moles of N2. Grams to moles, I use molar mass. And then moles of N2 to moles of N. To figure out components of a molecule within a whole molecule, I use subscripts, and then I need to get into individual atoms, moles of N to just individual atoms of N, and to find individual things in a mole, I use Avogadro's number. All right, so let's see how I'd set that up. I'm going to start with 5 grams of nitrogen, and I see I'm going to need to find the molar mass of nitrogen, which might be easier to do before you even start doing your dimensional analysis. I'm actually going to switch the order here just so we have the molar mass done before we jump into our dimensional analysis. So nitrogen, I find it on the periodic table. It has a molar mass of 14.01, and there's 2 nitrogen atoms in every N2. And so that's going to give me a molar mass of 28.02 grams per mole. All right, so I have, jumping back down to my dimensional analysis, I have 5.0 grams of N2. Now I want to get into moles of N2. So I always do units on the bottom. If grams of N2 are what I'm starting with, I need the same unit on the bottom. Moles of N2 on top. Now I do numbers. For every 1 mole of N2, I have 28.02 grams of N2. All right, next conversion factor. Moles of N2 are on the bottom, so moles, or are on top, excuse me, so moles of N2 are going to go on the bottom in my next conversion factor. I then see I need to get into moles of just N because I'm trying to get information about just single nitrogen atoms. So for every 1 mole of N2, I have 2 moles of nitrogen atoms. Now I'm in the unit moles of nitrogen atoms, which is kind of helpful to me, but what I really need to finally get into is just individual atoms, not moles of atoms, not counting by moles, but counting by individual atoms. So moles of N is on top, that means moles of N goes on the bottom, and N atoms, we can even write out the word atoms if you like, go on top. For every 1 mole of nitrogen atoms, there's 6.02 times 10 to the 23rd nitrogen atoms. Again, for every 1 mole of anything, there's 6.02 times 10 to the 23rd of that thing. Let's double check that my units cancel. Grams cancels with grams. Moles of N2 cancels with moles of N2. Moles of N cancels with moles of N. And I end up in nitrogen atoms. All right, I'm going to go ahead and throw this into my calculator and get an answer. So I'm going to do 5 times 1 divided by 28.02 times 2 divided by 1 and times 6.02 e to the 23, which is how I put that into my calculator, divided by 1. And I'm going to get 2.15 times 10 to the 23rd nitrogen atoms, individual nitrogen atoms. All right, very good. And then question A, how many moles of nitrogen atoms are present? Well, that's going to be that same work, just stopping right here to end up in just moles of N. And so that will be 0.357 moles of nitrogen atoms. So I can either count by moles or I can count by individual atoms. All right, I hope that helps with number 6. Number 9. All right, next problem. Here we go. So, in 10 grams of barium nitrate, how many nitrate ions are present? All right, barium nitrate. My first job is to find the formula for barium nitrate. I should remember nitrate NO3 minus. That's one of those common polyatomic ions that I have memorized, NO3 minus. Barium, I see, is right here. So barium, when barium forms an ion, it forms a Ba2 plus ion because it is in column 2 of the periodic table, has 2 valence electrons. So it tends to lose those 2 valence electrons and form a 2 plus ion. All right, so barium, when it forms an ion, will be, not Na, sorry, Ba2 plus. So barium nitrate is BaNO3 2 is the compound I would make because NO3 is 1 minus, Ba is 2 plus. So in order to make a neutral compound, I need 2 nitrate ions for every 1 barium ion. All right, so it's asking me in 10 grams of barium nitrate, how many individual nitrate ions are present? So my starting unit is grams of BaNO3 2. My final unit is individual nitrate ions. So my conversion factor, well, I'm starting in grams, so I'm always going to go to moles because moles are how I compare things. So grams of BaNO3 to 2 moles of BaNO3 2, and that's going to be molar mass. And now I need to do moles of BaNO3 to moles of, I'm interested in just nitrate, so moles of just nitrate, and that's going to be the subscripts. Part of something in a whole molecule, I use subscripts. All right, and now I'm going to be in moles of nitrate, and I need to get into individual nitrate ions, so I'm going to do NO3 minus, just individual ions, and that, of course, will be Avogadro's number. All right, so let's go ahead and find the molar mass of barium nitrate, since we will need it, of BaNO3 2. So Ba is right here, and I've circled over it, 137.33. Do make sure, please, that you are using the periodic table provided to you in the data booklet. Otherwise, you'll be off by 0.1 or 0.2, and that could cause you to not match up with the mark scheme, which would be unfortunate. O is 16 times 6, all right, so 14.01 times 2, 16 times 6, all right, and let's put this into our calculator, 37.3 plus 28.02 plus 16 times 6 gives me 261.32 grams per mole for barium nitrate. I'm going to go ahead and do just nitrate as well, since we'll need it, because we'll need the mass of nitrate ions. So while I'm doing this, I'm going to find the molar mass for just nitrate, and 14.01, and nitrate is NO3, so 16 times 3, and so here we have 14.01 plus 16 times 3 is 62.01. All right, grams per mole. Okay, so let's do my dimensional analysis. So these molar masses I'll need as I do it. I'm going to start with 10 grams of barium nitrate. And my first conversion is grams to moles, so 261.02 0.32 grams of BaNO3 2 times 1 mole of BaNO3 2. Beautiful. And now we're going to do moles of barium nitrate to moles of just nitrate. So in every 1 mole of BaNO3 2, I have 2 moles of NO3 minus, 2 moles of the ion, and one more conversion factor. Moles of NO3 minus are on top, so moles of NO3 minus need to go on the bottom. And then converting into individual NO3 minus ions, so 1 mole is 6.02 times 10 to the 23rd. Thanks. All right, and now I'm just going to put this into my calculator. 10 times 1 divided by 261.32 times 2 times 6.02 e to the 23rd. And I get 4.61 times 10 to the 22 individual NO3 minus ions. All right, I then need to find the mass of those. So I'm actually just going to stop my dimensional analysis here to find moles. And let me actually show that full thing. So I will have 10 grams of BaNO3 2 times 261.32 grams, 1 mole of BaNO3 2. So same process as before, times 1 mole BaNO3 2 moles of NO3 minus. Same process as before, except this time I'm going to end with mass. So 1 mole of NO3 minus, and I'm going to use the molar mass I found right at the beginning, 62.01 grams of NO3 minus is equal to. And make sure you put everything into your calculator. Don't round early, so don't find a number that's rounded and then put it into a second calculation. And this is going to give me 4.75 grams of NO3 minus. And that makes sense to me. NO3 minus is 62.01. And so it would, in terms of molar mass, and so it would be a little less than half of my total sample because barium is heavier. All right. Okay, one more that you asked me to go over, and that's number 11. If 5 grams of solid magnesium burns in oxygen to produce magnesium oxide, how many grams of product are made? So when there's a reaction, I always start by writing out the reaction. So I have magnesium solid plus oxygen gas yields magnesium oxide. Mg forms an Mg2 plus ion. Oxygen forms a 2 minus ion. So I make MgO. And MgO would likely be a solid. And now I just need to balance my equation. 2 and 2. And now I'm balanced. Great. So my starting unit is grams of magnesium. My final unit is grams of product, which in this case is going to be magnesium oxide. That's what I make when I combine magnesium and oxygen. And my conversion factors in order to get there will be, I'm starting in grams of magnesium. Grams is never that helpful. I always need to go into moles. And I'll use molar mass, of course, to go grams to moles. Moles of magnesium. I'm interested in magnesium oxide, so I can convert to moles of magnesium oxide. That's going to be coefficients. If I'm comparing one thing in a reaction to another thing in a reaction, I use coefficients. And then I need to go moles of magnesium oxide, 2 grams of magnesium oxide, and moles to grams is always molar mass. All right, so let's go ahead and get that molar mass for magnesium oxide. And that's going to be, magnesium is 24.7 0.31. Oxygen is 16. And so let's put this into our calculator. 24.31 plus 16, 40.31 grams per mole of magnesium oxide. And now we can set up our conversion factors. So I have 5 grams of magnesium times 24.31 grams of magnesium, 1 mole of magnesium times 15 grams to moles. I now have moles of magnesium to moles of magnesium oxide, and I could simplify, but the coefficients are 2 and 2, so I'll just leave it as 2 and 2. And now I just need to get into grams of magnesium oxide. So for every 1 mole of MgO, I have 40.31 grams of MgO, and my units, I can cancel them all out, and I see I really do end up in grams of MgO. Now I just put this whole thing into my calculator. 24.31 times 40.31, and the answer I got here was 8.29 grams of MgO. How many moles of oxygen were required? Well, I'm going to start that in exactly the same way. I could start with the 8.29 grams of magnesium oxide as long as I leave it in my calculator. Actually, I'm just going to rewrite it. So I could start with this as long as I leave the number in my calculator and I use the answer function, or I could go back to the 5 grams. It doesn't matter. You can compare any part of a reaction to any other part of the reaction. So I always want to get everything into moles if I need to compare, because moles are how I compare between substances. And let's see, I have 2 moles. Oh, sorry. Yep. 2 moles of magnesium. I need moles of oxygen for every 1 mole of oxygen. So I'm comparing between reactants. Whenever I compare between things in a reaction, I use coefficients. There's no coefficient next to oxygen, so I assume a coefficient of 1. And now I just put that into my calculator. And I get 0.103 moles of oxygen. All right, I hope that helped. Thanks for watching. Have a good day.